Welcome to Brain Vision.
The acceleration of the flea is 0 when its velocity is no longer changing. Looking at the graph, we see that this is from approximately 1.25 milliseconds onward. So for part A, yes, after 1.25 milliseconds, because the velocity is not changing. Next, we want to find the maximum height that the flea reached in the first 2.5 milliseconds. Well, the maximum height that the flea reached, if we have a velocity versus time graph, that's just going to be the area under the curve. Problem is, though, that one axis is in centimeters per second and the other one is in milliseconds. So we'd have to convert these to similar units. So let's see, for the diagonal part of this, we know that the area of a triangle is base times height times half. The height of this is about 130 centimeters per second, which converted to meters is 1.3 meters. And the width of this is 1.25 milliseconds, which to meters is 0.00125 seconds. And then base times height times half times 0.5. That's just for the triangular part. Now adding the square part of the flat part of the curve, we get, let's see, well, that's just the area of a square, so that's just going to be 1.3 or 130 centimeters. The area of a square is just base times height times 1.25 milliseconds, or 0.00125 seconds. Putting this all together, gives a maximum height that the flea reached in the first 2.5 milliseconds of 0.00, and let's see, go two significant figures. So 0.0024 meters, which is equal to 2.4 millimeters. Now we want to find the flea's acceleration at various points. So first we want to find its acceleration at 0.5 milliseconds. And at 0.5 milliseconds, well, first of all, we know that acceleration is just change in velocity for change in time. Then the acceleration at 0.5 milliseconds is going to be equal to 0.5 minus 0. Actually, wait, it should be should be about actually 30 centimeters per second, which is 0.3 meters. Minus 0 meters per second, that's the speed at the beginning. All that divided by 0.0005 seconds. Giving us an answer of 600 meters per second squared. Now its acceleration at 1 millisecond. We can approximate that as, let's see, we can do 0.8, so 80 centimeters per second, minus 0.5 meters per second, divided by 5 milliseconds. Again, gives us an answer of 600 meters per second squared. Now it looks like 1 millisecond might be a little bit more, or a little bit steeper in its acceleration, so a little bit greater acceleration, but they're approximately equal. Finally, at 1.5 milliseconds, we see that the acceleration is the velocity is no longer changing; it's flat. So the acceleration is now 0. Finally, for part D, you want to find the height at 3 different points. And this is going to be a lot like part part B, except we're just not going to add up the total area under the curve. We're going to only add it up to the relevant time. So at 0.5 milliseconds, the area under the curve is just, well, the area of a triangle again is 1/2 base times height. The height is 30 centimeters, which is 0.3 meters, times 0.0005 seconds, times half. And that's going to give a height of entering this in on my calculator, 0.075 millimeters. Height at 1 second, similarly, is going to be about 80 centimeters, or 0.8 meters, times 1 millisecond times half. Look at us. .4 millimeters. And finally at 1.5, well, we can use our part in the first one. We know, part B, just to get the triangle from 0 to 1.25 milliseconds. We found that area with just 0.000812.5 meters. And then let's add the last quarter millisecond, going from, let's see, say 130, 1.3 meters, times 0.00. Oh wait, we want just 0.25 milliseconds. 3 zeros. And that's going to be equal to moment, I have to put this in my calculator. 1.14